This is my Physics 2 Lab 3. The purpose of this lab is to use the principles of energy conservation, otherwise known as the loop rule, and current conservation, otherwise known as charge conservation. We will predict the behavior of circuits containing resistors in series and parallel, and use multimeters to measure the actual values of conventional current and potential differences in the current circuits, and examine the behavior of ohmic resistors and capacitors. Using the principles of energy conservation in a virtual setting, simulations of direct and RC circuits were done of these same circuits in an ideal environment. The fundamental principles contained in this lab are conservation of energy and charge, the loop rule, the node rule, steady-state circuits, Ohm's law, and RC circuits. A preview of our results is that the values gathered match with the theoretical values calculated using given formulas shown on our right. In this lab, the system is the circuit, while the surroundings is everything else in the universe, which is assumed to have a net zero effect. Rather than using a real-life model for this lab, we used a PHYS simulation, which is much more accurate and easier to work with. Because of this, the assumptions we made are that the resistance of the wires is negligible, and the resistance of the tools of the lab is also negligible, such as the voltmeter and ammeter. In part 1 of the lab, the given circuit on the right is created, and our prediction is that the current at location 1 at the top shown is equal to the current on the bottom. This turned out to be true, but we used the resistance and calculated the theoretical I, and that turned out to be the same answer when we used the ammeter. A more descriptive version of this circuit is shown here, labeled with parts. This graph shows the change in voltage over different parts of the circuit. It's built up over the set of 2 batteries, which add 1.5 volts each, and then it stays constant throughout the wire, as it's assumed that the resistance of the wire is 0. It then drops partially because of the 47 ohms resistor, and then drops all the way down to 0 the rest of the voltage because of the 100 ohm resistor. When connected to the 100 ohm resistor in parallel, the current reads 0.6 amperes at this point. Using the measurements from the given tools, we were able to figure out that the resistance from each of the labeled resistors is actually equivalent to what it labels, with the only differences 48 to 47 and 102 to 100 being the result of rounding. In part 2 of the lab, we charged a capacitor of 200 microfarads and using different bulbs. When the 10 ohm bulb is used, the capacitor takes around 10 seconds to discharge once disconnected from the battery, while it takes around 18 seconds to discharge with the 20 ohm bulb, both of which are very similar to the theoretical values. Using the formulas shown on the left, data for delta V and the natural log of delta V over the original voltage is shown here, with a perfectly linear trend as described on the graph on the right, resulting as when graphed against time. Because this lab was virtual, very little could cause potential errors. If the real-life lab had been done, potential errors would include incorrect wiring, unstable circuit connections, and bad readings via voltmeters and ammeters. These would have applied if I had done the in-person lab in the lab room as opposed to the virtual lab offered by this assignment. A picture of a potential voltmeter that I could have used is shown on the right, along with a 9-volt battery. First question, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about the real ammeter and how would it have affected the circuits you hooked it up to? In real life, ammeters have some small resistance, and therefore the theoretical measurement that it should give is a lower measurement for amps than the theoretical ammeter gave. It would also be a less accurate measurement because of different outside factors that could affect it, while in this lab, the other stuff could not have affected our theoretical ammeter. Last but not least, the second question, if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor to reach full charge? Would this happen in real life? Full charge would be reached immediately because of 0 resistance in our theoretical model, but in real life, this would take some time as the wires would have some level of resistance, slowing the charging of the capacitor, and therefore our graph would not be perfectly linear anymore. Thank you.